Hello, everyone. Welcome to another Q&A about future of science and technology. Uh, these are always fun for me because the questions you guys ask get me to think more about the future, which is interesting. Let's see. We have a question here. We have a bunch of questions saved up. We have one from Anon asking, can you see optics being used eventually to do what quantum computing claims it can do? Oh boy. Well, first thing, let's talk a little bit about quantum computing. I mean, in a strange turn of history, I worked on quantum computing in the early 1980s, actually in part with Dick Feynman, a physicist who was interested in such things. And I realized recently that I wrote a kind of referee report on the sort of the first paper about quantum Turing machines, telling the author that I thought their paper was extremely hard to understand and suggesting a better way to describe what was going on, which the author ignored. And that was sort of lost forever. It's a pity that my explanation of quantum Turing machines didn't make it out into the world in 1982 or so, but I didn't think it was that interesting. Well, quantum computing then, kind of the idea of let's see whether we can do computing kinds of things at a quantum level became, investigated. David Deutsch, for example, started studying quantum gates and quantum circuits and so on. And then in that was sort of an interesting thing. It kind of had relationships to quantum logic, sort of generalizations of logic that related to the formalism of quantum mechanics, things like this. Then the real boost came with Shor's algorithm in the early 90s, I guess, that made the claim that a quantum computer could factor numbers faster than a classical computer could. I think the big picture that has been somewhat obscured by the formalism of quantum mechanics, but the big picture about what a quantum computer can do is it is sort of core to the idea of quantum mechanics is that many things are happening in parallel, but we only get to observe sort of the aggregate probabilities of what took place. And so that many things happen in parallel gives one the possibility of doing computations more efficiently. Like if you're factoring a number in parallel, you could try dividing the number by lots and lots of different possible divisors. And normally in the world as we normally think about it in classical physics, you'd have to do all those trial divisions sequentially. But in quantum mechanics, you can get to do all of them in parallel. The thing that's the big sort of problem of quantum mechanics in terms of its use for computing is that, yes, all those things can happen in parallel, but we want to know the answer. And that requires somehow knitting together all of those different threads of underlying quantum history into something that we can say that's the answer. In the formalism of quantum mechanics from the 1930s and so on, this idea of measurement was just a mathematical operation. It's just, yes, you have all those threads, you have all those superpositions of possible states of the universe and so on. And it's then just the measurement operator is applied, a mathematical operator where it projects it into a definite answer. Question is, how does that actually work in practice? In practice, that's a thing where typically you're taking a little tiny quantum effect and you're somehow amplifying it to the point where we humans can sort of sense it, where we can actually do things with that, with whatever it was that was the sort of outcome that came from that little sort of quantum effect underneath. Well, this process of what does it take to do measurement has never been properly formalized. We've been trying to do it a bit in the context of our physics project. Lots of progress actually happening in various directions there. But the main point is that, yes, you can work out sort of what will happen in principle with sort of measurement as a mathematical operation. What will happen in practice is a much harder problem. And this is one of the things where, how does that show up when you actually make a quantum computer? It shows up usually in the fact that you just can't quite get that answer. There's too much noise. There's the phenomenon of decoherence, where you sort of think you're maintaining a quantum state, but it's decaying with time. These are things where people keep on pushing, oh, we're going to use error correction. We're going to gradually improve kind of the extent to which we can get an answer from this sort of underlying kind of many threads of possibilities that exist sort of in sort of the underlying physics of the quantum mechanics. This problem the problem of sort of what does it take to get an answer, it's really not a solved problem. It's to some extent, it seems like an engineering problem. It seems like the kind of thing where if you just were to, you think about a telescope or something, polish the mirror better, then the telescope would work better. But I don't think it actually is that way. I think it's not really just an engineering problem. My own guess is that there's sort of a fundamental physics limitation associated with the kind of this measurement process in quantum mechanics, possibly related to a thing we call the maximum entanglement speed in our physics project, but something that's sort of a fundamental limitation on what you can do with sort of quantum measurements of complicated systems. I have to say, it's kind of ironic that I thought that back in the early 1980s, although the kind of ways to think about that and the formalism we had to think about those things wasn't as sophisticated then as it is today, but it's still the same problem. And it's the problem that you find out when you kind of go to the back office, when you visit a quantum computing company type thing. The engineers are like, well, yes, we're having some trouble actually, getting the performance we want to get. I think that's a fundamental physics problem, not a sort of engineering, lack of engineering effort. I don't think it's the case that, like in the semiconductor industry, where there's just been sort of progressive improvement in how small you can make the features on chips, how fast you can run chips. Well, that's somewhat peaked out, but there's sort of a bunch of engineering improvement with some occasional physics added, but mostly it's engineering. I think in the quantum computing case, there's a bit more that's really a physics limitation, more like when you're building telescopes, the resolution of a telescope is ultimately limited by the physics of diffraction, not by how well you polish the mirror in the telescope. So where does that leave sort of what will happen with quantum computing? I think that the kind of the effort to study the physics of quantum level processes is very worthwhile. I think that the formalism of quantum mechanics of thinking about doing computations in parallel and so on, and the quantum version of that, that's also perfectly worthwhile and useful. I think that sort of having the big banner of we achieved quantum computing is a little bit, is a good marketing message, but I don't think it's reality. I think that it's sort of a funny situation right now because there's ultimately a lot of energy being put into quantum computing because people are sort of worried if it turns out that Shor's algorithm can suddenly factor numbers really efficiently, break out of the almost exponential amount of effort that it seems to take to factor numbers. If you can break out of that, then all the number factoring based public key cryptography in the world will crumble in a day when somebody makes that quantum computer that can factor numbers quickly in a routine fashion. The question is that going to happen, or is it like saying, will we invent warp drive and be able to, or go faster than light and zip around and not have to invest in airplanes because we can just zip from place to place faster than light or whatever? I think it's one of these things where my own guess is that it really isn't a thing that's possible based on kind of the way that we are in terms of what we want and definite answers from these systems that are sort of following many threads of history and so on. But I think what sort of survives from the whole kind of effort to investigate kind of quantum computing, one thing that survives is the possibility of radically new physics technologies for implementing computing. I mean, we know, and even my own efforts and the principle of computational equivalence and so on, give one a great deal of confidence that computation is possible in many kinds of systems. It's not just semiconductors and electronics that do computation. It's molecular scale systems do computation. Systems where you can imagine doing computation with fluids. You can imagine doing all kinds of computation. It's sometimes a difficult problem to kind of set up the initial conditions for the computation and read out the results. But many things in the natural world, in the physical world, compute. And the question of which ones are convenient to use technologically is one that is sort of an engineering problem. And a lot of effort has been put into quantum computing of investigating different sort of physical substrates for computation. And that seems like a worthwhile thing. And it's whether those computations are operating right down the level where you have to be thinking about quantum mechanics, or whether they're just operating at a scale that's smaller, faster, whatever, than semiconductors. The latter is enough to be very interesting. So one of the places where that comes up is optical computing, whether one can use photons rather than electrons as a sort of substrate for computation. I mean, it's worth realizing that there are a variety of substrates for computation that sort of work in a little bit the same way. Like in biology, we can think of sort of flows of molecules, flows of ions, things like that, as well as flows of electrons, as being things where biological systems are sort of computing at a molecular scale, but the substrate that they're using is more like molecules than it is like specifically electrons. But the other possibility is using photons as the substrate, as the sort of carriers of information in computation. Photons are used all the time as carriers of information in lots of situations, most notably in things like fiber optics. That is sort of the standard these days for communications, whether it's the internet or whether it's in server farms or whatever else. That's kind of the way information is transmitted, is with photons going through glass fibers for fiber optics. But the question is, can you compute with this? Can you make those photons not just be transmitted from place A to place B, but actually interact in some way that does a computation? That's difficult. One of the things that made electronic computation possible was the discovery that you could make electronic switches. First, those were vacuum tubes, later transistors, but that's what, a microprocessor is billions of little switches made up of transistors, of field effect transistors implemented with semiconductors. That's sort of a big question. Can you do that with photons? Can you make an optical switch where, and sometimes when people use the term optical switch, they mean something where there's electrical input and it switches whether a photon can go through or not. What I'm talking about here is a photon switched sort of gate that determines whether a photon can go through. We don't know how to make those yet. We know for very intense light, there are ways to make switch-like things, but it requires that you're sort of pumping so much light into something that you're saturating the amount of light that atoms can absorb and so on. And that's far, if you had to do that, you couldn't make something small and efficient and so on. So it's sort of the unsolved problem of optical computing at some level is to make kind of a photon to photon switch. If that was done, then immediately you could start switching lots of technology from electrons to photons. Now, is there fundamentally quantum mechanics there? We're used to photons having interference patterns and so on. We're used to kind of the wave character of photons. We're more used to that than we're used to the wave character of electrons. Electrons, as a result of quantum mechanics, also have a wave character. At the level of the actual way that microprocessors are made, with feature sizes of a few nanometers and things like this, the wave nature of electrons does start to matter. And certainly in the etching of semiconductors, it matters a lot that there's at least with electron beams and so on, it matters that there's a wave character of the electrons and such like. But in terms of sort of the fanciest effects of quantum mechanics, well, as a practical matter, when you figure out how to make a microprocessor, you do have to pay attention to quantum mechanics in several different ways, in the ways that the actual semiconductor works, in the ways that you're etching things out, and so on. And in the way but you're not having to pay attention to it at the level of kind of thinking about, oh, I'm doing a quantum algorithm rather than a traditional classical algorithm with classical logic and so on. The same will be true of photonic computation. There's a lot that will be, once one can do that, if it's even possible to make photonic switches, you would expect to sort of implement the same kinds of things you do in classical computers and classical logic. Could you make use of the wave nature of photons and sort of interference patterns and so on? I'm not sure. Probably yes. Probably using some of the same formalism as in quantum mechanics, although the effects don't have to be sort of the really deep effects of quantum mechanics. I mean, it's worth saying, by the way, that there's sort of a different issue, which is when you're dealing with a microprocessor and you have electrons going from here to there, they go at a certain speed. They go at, I don't know how fast it is, maybe a third of the speed of light or something. If you have photons, well, photons in a piece of glass go at 2/3 of the speed of light. So, there are places where it matters to have signals transmitted optically rather than electronically, although that's not as dramatic as an effect as to have sort of the whole thing operate photonically. But I think, one of the things that I suspected for a while was that sort of eventually quantum computing would sort of turn into optical computing and then sort of victory will be declared type thing. I'm not quite sure that that's quite what's going to happen at this point, because I think some sort of basic ways in which optics can be used in computing, those are already happening. The problem of inventing the photonic switch is still out there in the future and might not even be possible. I mean, it requires that there be some strange kind of material that will deal with individual photons and will sort of have the switching behavior. One just doesn't know such a thing. That such a thing exists or even could exist. I have to say, in terms of quantum computing and so on, I think sort of in the quantum realm, the thing that seems to be the most immediately useful is quantum sensors, where one's using effects that are from sort of foundational quantum mechanics to make very sensitive measurements of things. Most obvious thing is magnetic fields, where there are sort of flux quanta that you can have where those are sort of the very lowest level, the very smallest units of kind of magnetic field that are sort of quantized, and you can start measuring those quantum flux units effectively, and that allows you to make a very sensitive magnetometer. There may be many uses for that. Certainly some that have already come into existence are things like the Earth's magnetic field changes depending on where you are. And so you can use that as an alternative to GPS as a sort of local way of measuring where you are on the Earth's surface. And there are things one can imagine with MRI, for example, other kinds of places where actually not so much that, maybe MEG, magnetic encephalography, where you're measuring magnetic effects of nerve cell firings rather than electrical effects and so on. There are all kinds of places where you can imagine that very sensitive magnetometers might be important. I don't think we know yet what all those places are, but that's an example of something that seems to be coming from sort of the quantum realm. And there may be other kinds of very sensitive measurement techniques that can be used that sort of come out of quantum effects and so on. So a few thoughts about that. Let's see. Well, there's a question here. Okay, let's look at a few of these about quantum computing. Hannah, do you think quantum computing will actually change everyday life, or will it just be for specialists? Well, right now it's not changing anything. I mean, in sort of the spin-offs from quantum computing of sort of better devices for doing computing will be probably incremental change, probably just sort of slowly introducing that technology in place of existing microprocessors. I mean, it's conceivable that there will be a big jump, that suddenly it will be possible to do computing 1,000 times faster or more. I'm don't immediately see that. I think it's more likely that we'll be able to do computing at a smaller, more molecular scale, more like the way biology seems to do it. Biological, some aspects of biology. I mean, in brains, that's not what's happening. There are great big neurons in brains. But at the level of molecules, the sort of dance of molecules that makes up life, that's more like actual computing done at the molecular scale. But in a sense, what's happening there is it's computing, but we don't know what it's computing other than sort of keep you, alive and happy, so to speak. Because it's sort of a dance of molecules that are achieving things that we can simulate on a computer and say we're doing computing there. But what if we say, I want that dance of molecules to compute this math problem that I'm trying to solve? We don't know how to plug that together yet. But I think it's an interesting question. If computing suddenly got 1,000 times faster, what kinds of things could we do? It's been interesting over the course of years. I've been doing language design now for 45 years or something, And the things that you can sort of take for granted that computers will be able to do have moved a bit over those years. I mean, the speed of computers has changed dramatically over those years. Let me give you an example. If you have a user interface and you say, how much can I compute? Can I just write this complicated program and have that whole program run in the time it takes me to notice that I move my finger on some slider? Well, the answer is one can do that now. That was too heavy a lift, let's say 40 years ago. And so that's something where sort of faster computing makes that possible. Video conferencing, for example, another case where sort of in a sense, there's a fixed time horizon, a fixed time interval that's determined by our ability to notice whether a video is, whether something is really moving in a video, maybe 1/15th of a second, something like this. And the question then is computing fast enough that in that 1/15th of a second, we can transmit that video frame and so on? And the answer is there came a time when that happened. There came a time when we sort of were able to get realistic video transmitted, encoded by a computer, transmitted, and so on. I mean, it's the same kind of thing that happened, well, in audio much earlier, in video now. I suppose the next kinds of things are synthesizing video in real time, being able to use kind of AI techniques and others to kind of create the scene in real time. Already this is happening a whole bunch in video games, but there's more of that one can imagine happening. I mean, there's a lot of things where it's interesting to wonder what one would be able to do if one could compute 1,000 times faster. And what kinds of things were things that, well, even today, there are so many things that get done by computers where in the past it would have been you couldn't use a computer for that. It would just take, it's crazy to waste that much computation. I mean, the typical computer these days, most of what it does is be idle, and it's running an idle loop. In the past, when computers were much younger, it's like every moment of computer time has to be used for something. It's not the concept, or even the concept that you can watch a movie on your computer would have seemed crazy, but until it became the case that it was so cheap to do computing that you might as well just have that video playing on your computer screen, not on a custom television or whatever. So it's an interesting question. What else we could do if I think sort of a lot of figuring out of predicting what's going to happen in the world that might become possible. And when I say predicting what might happen in the world, I mean at a very local scale that might become possible if you had a lot more compute at your disposal. Would you be able to do, I mean, the kinds of things that are now done with things like machine learning training and so on? Yeah, those will become faster to do, and it might mean that you could do more of traditional current machine learning training on the fly. I don't happen to believe that the current huge investments made in machine learning will still need to be made when we figured out more about how machine learning really works. But even if you assume that that's what you're doing, being able to compute 1,000 times faster brings into kind of personal range some of the kinds of things which in the current time are only accessible to sort of large companies spending with huge investments in these kinds of things. Let's see. Pedro asks, what could quantum computing bring to AI and machine learning? Well, first of all, as I keep on saying, I don't think the big flag of quantum computing is going to work out. But the ideas of quantum computing, that's an interesting question. And you could say theoretically, if quantum computing happened, what would occur? But by the way, coming back to the previous question about quantum computing changing everyday life, if it really slam dunk worked in a way that I think it won't, then sort of the way cryptography is done would change. People are talking a lot about, quantum safe algorithms. I think this is a very, difficult thing to discuss because it happens that there's this one example from the 1990s of a cryptography-related algorithm which is kind of crushed theoretically by quantum mechanics. And you could say, well, what about all the other things? There are not that many of them, but all the other kinds of methods that people have invented for doing public key cryptography, for example. Well, we don't happen to know that those can be crushed by quantum computing. even if we had the theoretical, even if the theoretical side of quantum computing worked out the way that the theory kind of indicates that, well, it doesn't really indicate that it does. The theory, if you just believe the theory, which isn't the thing that relates to reality, it's all rather tenuous. And I think that the question of whether there are sort of quantum safe cryptography, again, it's a driver to study different types of cryptography using, I don't know, lattice methods or something, rather than using factoring integers, using questions about whether, well, the different kinds of mathematical problems. That's a perfectly reasonable thing to study. The fact that you say this is quantum safe, I think that's pretty tough to say. But what effect would it have on the world if somebody made that practical quantum computer and it, the day it happens, lots and lots of sort of computer security would just fall completely immediately. It would be replaced by other methods that sort of don't seem to be as attackable by quantum mechanics, if such things exist. Let me just make a few technical points here. So the big question is related to the P versus NP problem of computational complexity theory. The basic question is, if you can, there are computations that you can do fairly quickly. Like if you've got two n-digit numbers, you can multiply them together in a time that's about n. We know n log 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 n multiplication speed things for large n. So you can multiply numbers very, very quickly. If you if the numbers have n digits, you can multiply them in a time that's about n. If you ask, can you factor the number? The most obvious algorithms involve sort of testing every possible number less than, let's say, the square root of the number. And the size of the number is about 2 to the n, exponentially larger than the number of digits in the number. And so that means that that kind of strategy means that you will take exponentially long to do that factoring. Now, can you prove there's no better algorithm for factoring? No, you can't. Nobody knows how to do that. But for example, testing if a number is prime, there are actually fast algorithms that are of order the number of digits in the number, not the exponential of the number of digits in the number, to test whether a number is prime. But to factor a number, so far as we know, it's still roughly exponential in the number of digits. But proving that there's a lower bound, proving that there's no way to factor any faster than that, that's something nobody's been able to do. There is this notion of problems, well, like factoring as an example of a problem where once you've guessed the factors of the number, you can easily multiply them together and check that they're right. But the question is, how do you find those factors in the first place? And so one talks about two classes of problems, P problems, so-called polynomial time problems, where the difficulty of solving the problem goes up only like a polynomial in the size of the problem. So things like multiplication of n-digit numbers, it's a polynomial, it's of order n, the time to solve that problem. On the other hand, factoring is an NP problem, a problem that's a non-deterministic polynomial time problem. If you could guess the answer, then you could check it in polynomial time. The question is, can you find the answer? The P versus NP problem is the question, can you find the answer? If you can check it in polynomial time, does that mean you can also find it in polynomial time? Okay, so that's sort of the definition of that problem. It's sort of a core problem in computational complexity theory, is the class of problems that can be done non-deterministically in polynomial time, is that there are problems that are in NP that are not in P, that can be done non-deterministically in polynomial time, but not deterministically in polynomial time. And what was discovered in the early 1970s is this notion of NP completeness. There are problems where if you can do, where there are problems which are sort of equivalent in difficulty, where you can translate between them with only sort of a polynomial translation. So for example, things like various kinds of graph coloring problems, various kinds of problems about whether logic expressions can be satisfied, all sorts of kind of routing problems and so on. These are all examples of so-called NP-complete problems. If any one of those problems could be done in polynomial time, they could all be done in polynomial time because all those problems are complete for the class of NP problems. You can emulate encode any NP problem in terms of one of those problems. It's very similar to the thing that you can do with universal computers, where you can write a program for one computer that will emulate the behavior of another computer. The NP case is a more junior case because you're not doing arbitrary computation, you're just doing these non-deterministically polynomial time computations. So there are a class of problems known to be NP complete, a whole bunch of them. Factoring is not one of them. We don't actually know whether if you could solve factoring, it would allow you to solve other NP problems. If there's a chain of ifs, if you could build a quantum computer and it could then do factoring fast, then factoring would have sort of fallen below and then the question is, well, what does that mean for the other NP problems? Because basically all public key cryptography is based on the assumption that NP problems are hard, and in general. And so there's sort of this question of, well, what gets left if factoring falls? If an NP complete problem fell, they all fall. If factoring falls, it probably doesn't pull very many other problems with it. And certainly it better not pull any NP complete problems with it, because then you would have pulled all the NP complete problems. So that's kind of this question of sort of what happens, the mythical day where quantum computers break public key cryptography, factoring-based public key cryptography. Does that just mean everybody just migrates to another NP problem, maybe an NP complete problem? That's been a difficult thing in cryptography, to find a case where you can base the security of cryptography not just on an so-called NP hard problem, but actually on an NP complete problem. That hasn't been successfully done. We don't know how to sort of peg cryptography, the security of cryptography, to a complete NP problem. We only know how to do it to NP problems that aren't part of that pool of NP complete problems. Okay, anyway, long answer to that. But I was coming back to Pedro's question about what could quantum computing bring to AI and machine learning? I think one of the things that happens for example, an LLM, the main mission of an LLM is guess what the next token should be in a stream of output. So, you're always the LLM has been trained to work out what's the most likely next word in the sentence. I don't know, the cat sat on the blank, probably Matt type thing. It's always that's the mission of the LLM is to figure out what should the next word be. Now, usually in a typical application of an LLM, there's a whole it has worked out, of the 50,000 words in English, let's say, what are the probabilities that should be assigned to each of those words? And normally it just picks one particular word to use. Sometimes that so-called zero temperature, it's picking the word that it thinks is the most probable word. Usually for doing things like writing, essay responses and things, LLMs are set to temperatures of like 0.8 or something, where they are picking words we're picking somewhat at random these words with probabilities that are closely related to the probabilities the LLM thought that word would occur. They're not always just saying pick the winner, the most probable one. They're saying pick a word at random, weighted with the probabilities that the LLM assigned to it. But anyway, what's happening is you've got a single word that is being picked as the next word. What one would suspect from sort of the quantum idea is, well, don't just pick one word, look at sort of a whole range of possible words. Do the thing that we're describing quantum mechanics as doing. Don't just follow one path, follow a whole bunch of different paths that maybe branch and merge and do all those kinds of things. And so one can imagine sort of a quantum version of an LLM in which it is not just giving you that one string of words, but it's treeing out or all these possible sequences of words. And maybe it's doing that with some watching for whether it achieved some particular objective. So this kind of sort of the quantum idea could be a you've got many different things coming out of the LLM. Now, if you had a quantum brain, you could happily be reading off all those different threads of what was being said. The LLM would be saying many, many things. It would be speaking in LLM tongues or something in parallel, so to speak, many different things. And your quantum brain would be able to process all those different sort of threads of what was going on. But that's not how our brains actually work. We expect a single stream of words to come out, and somehow that's what we're looking for. Now, so then we might have something where we've got many sort of streams of words that are being generated internally by the LLM, but then we're picking the ones that satisfy some particular criterion. It's a little bit like what's happening in factoring numbers, where we can imagine having many threads going on there, and we say, let's look for a thread that satisfies the objectives we want. I noticed with GPT-5, for example, there's some capability to make the output follow a so-called context-free grammar. So that's saying, rather than having it be sort of a free-form thing where, yeah, it's roughly right, but it might not get, if it's writing a piece of code, it might not get the syntax of the code quite right. There's a way of constraining the output to precisely follow kind of the grammatical rules that say once you open a parenthesis, you've got to close a parenthesis. Once you've done this, et cetera, et cetera, et cetera. I think that's sort of going a little bit in this direction of, there are things that can happen. You're pruning the thing based on, you're pruning these possibilities, not just based on probabilities, but you're pruning them based on some structure that you're looking for. And maybe in some cases, you have to follow a thread forwards that eventually doesn't work out. You have to backtrack and follow another thread. One could also sort of pre-generate some of those threads, do them in parallel, and then be just throwing away the ones that don't satisfy the constraint that comes from this grammar that you've defined. Let's see. Gosh. Let's see. Following this, Evil is asking, what do you think about neuromorphic systems? I don't know. I mean, that was one of these buzzwords. There have been many of these kinds of make computing leverage what we know from nature in what happens in computing. I mean, in engineering, there have been some success stories, partial success stories, overtold success stories, undertold success stories about where we got a clue from nature about how to do a piece of engineering, whether it was sort of Velcro and the gecko feet, or whether it was aeroplanes and have wings, although they don't work the same way as bird wings, particularly in aeroplanes. Nature gives one all sorts of clues about how to do engineering. I think in the question, the whole idea of neural networks, for instance, did come from 100 years ago, basically, close to 100 years ago, did come from sort of thinking about how brains seem to work and then emulating those in what ended up being electronics and now in software and so on. That was sort of a from nature kind of idea. I mean, it's worth saying in terms of sort of getting ideas from nature for technology, the place where that happens just all the time is in life sciences. It's sort of embarrassing how many of the things which have been invented, whether it's nanopore technology for sequencing DNA, whether it's gene editing technology with CRISPR and so on, these things, we didn't invent these things. We found these things. CRISPR is part of the immune system of bacteria. Nanopores, oh gosh, where is that from? That's another biological mechanism. But there's a whole bunch of places in things related to the life sciences, things at molecular scales, where we didn't invent this stuff. We just found it. Same is true with a vast array of the drugs that have been discovered, the few thousand drugs that are out and about in circulation and so on. that the vast majority of those came from when they were not designed by sort of explicit human engineering effort. They were things found, oh, that's the bark of this tree and it does this, and et cetera, et cetera, et cetera. They were chemicals that had been produced by biological organisms, for example, and then we just sort of brought them in and used them. So it's sort of natural to say, well, what can we learn from biology? After all, it's been going a while, and it's had this process of adaptive evolution, which has got it a long way. And if we look at raw numbers, I think 10 to the 41 organisms I once estimated have lived in the history of life on Earth. It's That's a lot of organisms. It's not absolutely out of range of the kinds of things, the number of operations that computers can do, and so on. I mean, if we've got, let's say 100 billion computers in the world, that's 10 to the 11 computers doing, let's say, 10 to the 10 operations per second. That's 10 to the 21 operations per second. In a year, that's 10 to the 28 operations roughly. So we're getting up there, and obviously biological evolution has had a couple of billion years to have all those organisms exist and so on. But but it's also a very inefficient system for discovering things. What's my point? I mean, in a sense, we can expect that biology has been ahead of us in some ways, but it has many constraints in the way that it builds things. Proteins are just not that. They're wonderful and can do all kinds of things, but one imagines they're not the best way to do lots of engineering kinds of things. I mean, I think in my own efforts, I've done kind of the sort of pure abstract software analog of what biological evolution has often done. I've been sort of searching these spaces of possible programs, been doing that for years, finding all kinds of interesting things that you can, if you just sort of randomly go out into the computational universe of possible programs, you find things that you wouldn't actually find if you had to go down a path where you're always having to have a successful program. Because in biological evolution, you don't get to have, if you, the organism, die, you don't get to have children and pass on your genetic information. So it can't be the case. If you wanted to get to this place where there's this amazing discovery that was made in the way the biological organism is constructed, but to get to that place, you have to go through a kind of swamp of organisms that wouldn't make it. Biological evolution can't do that. I've actually studied in the last year or so, I've studied a lot about what biological evolution can and can't do. Different topic, maybe we shouldn't get into that now. But back to the question of sort of neuromorphic computing, I think the issue is to what extent can we emulate different aspects of how brains work and expect that to be useful? It's a key question, what matters in how brains work? For example, there was a time when people were trying to make proto-airplanes and they decided to put feathers on their wings because after all, birds have feathers on their wings and they successfully fly. Does it matter that you have feathers on the wings? Well, it turns out it doesn't matter. There are not a lot of airplanes that I've ever seen that have, in fact, I don't think I've ever seen an airplane with feathers on its wings. That just turned out not to be a key aspect of the problem of flight. So in the case of brains and kind of computational thinking like activity, to what extent is what aspect of human brains important? Well, what's become clear from sort of the success of things like LLMs is a lot isn't that important. We didn't know until LLMs came on the scene. We didn't really know. It could have been the case that there's some weird physical effects and so on in brains that we'd never really emulated in electronics and that were the killer thing we absolutely needed to be able to make a brain-like thing. I think we now know that that isn't the case. It's sort of all abstract software kinds of issues. It's not some magic new piece of sort of physical hardware. And I think that's sort of the sort of, at least what I remember of neuromorphic computing, a lot of it had to do with sort of things that were almost hardware tricks that one was emulating from biology, whether it was using continuous values for variables rather than the discrete things you have in bits and computers and so on. That's some, and I think the evidence now is that for the things we do that involve sort of thinking like processes, you just don't need that stuff. So it doesn't seem like it seems like it's one of these things where you're hewing too close to the actual biology and you don't need to. And because what you can build with electronics is a bit different from what we can build with biology, it's kind of like go with the stuff that can be just done with electronics. Just like if you were, building a metal bird is hard. That's just not what biology does. It doesn't make, pieces of aluminum with rivets in them. But it does fairly easily make bones and muscles and feathers and things. And so it's a different technology stack, and one should sort of pursue it in a different way. Let's see. Boy, a lot of interesting questions here. Prab is commenting, I keep noticing this thing with LLMs that they're clumsy with math, even though they keep saying it's so great. I don't know why they say it's so great. I mean, you can easily test it, and it's not. And it's not surprising that it's not. It's it's not for sort of the same reasons that we humans are not. We humans can do conceptual math if we really know what we're doing quite well. We humans are not to be expected to do detailed mathematical calculations in our minds. It's just not what we're built for. It's what computers are built for, but it's not what humans are built for, and it's not what neural nets are built for either. Let's see. Oh boy. So many. Um, well, Hilza is commenting about things like ChatGPT, about running some sort of logic on the input. Why don't they run the same engine on the output? Well, I think that the input is mostly constraining the kinds of things you can talk to it about. It's sort of a pre-censorship kind of thing. I think the output, there's similar kinds of things run, but this question about, is what you're saying, does what you're saying make sense? Well, what's the gold standard for that? It's in for things that involve computation, the gold standard is what the result of the computation was. You shouldn't be using a neural net to do that computation anyway. If the question is something which is a more vague kind of linguistic kind of thing, it's like, how do you tell that the answer was right? You can feed it to another LLM. That's what one often does. That's what we do for lots of things we're doing is you ask another LLM, did that first LLM do the right thing, and so on. But I think ultimately the thing that people have been doing a lot, we've tried some things with this, they haven't worked very well, where you're kind of getting the LLM to create something which you can then sort of check, did it meet this framework? I think there will be better success of that in the future, but I don't think that's the best use of LLMs. I think by the time you're trying to make something which has a sort of precise framework, you should be using computation to do that. And I think, I mean, this is a longer subject, but it's kind of the whole story of the best thing we can do, given what we know, is to link LLMs to basically the computational language that we've built to computation and to precise knowledge. That connection of the LLMs as kind of linguistic interface layer connected to precise computation and precise knowledge, that's a winning story. I think the idea that you're going to have a bigger neural net that will eventually sort of somehow magically reach that level of precision, it just isn't going to happen. And we can see that from things I've done. For example, I'm trying to understand the foundations of machine learning, but the sort of dynamics of the industry are such that there's a moment where people just don't want to hear that because it's a kind of a complicated flywheel of sort of investment and hope and enough performance to sort of keep things going and so on. But I think the thing we're observing is that these kinds of things about, can you make a neural net compute? The answer is no, and it isn't getting any better, and it's not going to get any better, and it's not the right thing anyway. because it's like saying, let's teach all the humans to do math or run code in their brains. Good luck with that. We humans don't do that. But, people like me have spent a lot of time building tools to let us humans get the leverage of doing that. I mean, it's just like saying, why don't we just teach humans to fly? Well, actually, that's just not something we can do. Better use airplanes or drones or whatever you're using to fly. Don't try and teach the humans to fly. And I think it's the same kind of thing with neural nets. You can, we don't teach humans to run code in their brains. There's no class that teaches people running code in your brains. Similarly, we don't get to teach neural nets how to run code in their brains because it's just not the kind of thing that a system like that does. However, we can make great use of the more precise, more engineered kinds of things that, like, I've spent the last, 45 years building to supplement that and achieve things that would not be achievable with the pure sort of brain-like neural net on its own. And that's surely the future, although it's taking a bit longer to arrive in a kind of strong way than I might have hoped. But the future always takes a bit longer to arrive than one hopes. I think it's been very obvious since sort of pretty much the day ChatGPT came out that this is sort of the dynamic one should have. And and we had built versions of this within a couple of months of ChatGPT coming out, but it's still not a sort of a clearly mainstream thing for various, I think, industry pathology reasons right now, and I suspect that will eventually change. Let's see. Oh boy, so many interesting questions. Okay, there's a question, different direction from Test. Will DIY genetic engineering be popular in the next few years, e.g. to grow stripey carrots? I have thought for decades that the time when I really know that we have understood sort of genetic engineering is when the fruit you buy in a grocery store already has a barcode on it that grew with the fruit. Okay, that was a silly thing to think about, but I'd sort of wondered that like 30 years ago or something. And instead of anybody having to put that sticker on the peach or something, just have the peach naturally grow a barcode that says kind of I'm a peach. Now, of course, in modern times, image recognition could perfectly well establish what kind of fruit it was. I didn't think of that 30 years ago. How far will sort of cute genetic engineering for these kinds of things go? I recently tried to buy a glow-in-the-dark plant that has jellyfish genes in it. My assistant who took delivery of this thing, it died in her care. I never saw it. She said it was very dim. It didn't really, you had to be in an incredibly darkened room to see this plant glow in the dark. But I've always thought that things like sort of the test of weird genetic modification fashion is when humans start sort of modifying their genomes to have sort of glow in the dark features and so on for themselves. I think there are lots of weird things like that one can imagine. It is not a trivial problem because going from the genetic program of an organism to the kind of, well, glow in the dark is easy. That's just add GFP protein to things. But doing something like putting a barcode on the peach or stripy carrots or whatever, these are not so easy because the challenge is to go from the program that is on the DNA to what's that going to make. It's something where people had imagined, I don't know, 15 years ago or something now, when the Human Genome Project got done, that we'd be able to sort of get our programs and then immediately read off all these things of medical significance or other kinds of significance directly from our genome. The main message has been things are more complicated than you can possibly imagine. I was actually happened to just be looking recently at just genetic encoding of eye color, which I thought was a fairly straightforward trait that will be determined just by one kind of base pair or something in the genome. No, it's actually much more complicated than that. And that's been the story of almost everything. no, it's much more complicated than that. So that means if you say, I want to make this thing end up with stripes, there will typically be this very complicated dance of different genes interacting with each other that will lead to the thing having stripes. There are cases where one can make one simple modification and something happens, something goes wrong. But I think the more general case, if you're trying to arrange to have it have some particular form, it is going to be a complicated dance of many genes, and we don't really completely know how to do that. In fact, some of the work that I've done in sort of foundations of biological evolution and foundations of medicine, looking at kind of simple computational models of these things, makes it clear why that's hard. There are certain things where you can sort of artificially evolve, you can change the program by sort of artificial evolution to get to the point where it does some kinds of things. But if you say, I want this pattern to have this very complicated form that has these specific characteristics, it's hard to even get to that, even with artificial biological evolution. I mean, the reason biological evolution works at all is that the fitness criteria for what will survive are fairly coarse. They're not things that say, in order to survive as a plant, you have to be able to compute the millionth prime. They're much sort of coarser kinds of criteria. And I think if saying I want the thing to have a particular shape or something, or a particular pigmentation pattern, that's a pretty difficult thing to achieve. And the idea that you can just go in as a sort of genetic designer and figure out how to get the organism to look like that is not yet a reality. And I think it's going to be a difficult thing. I think that there will be particular sort of engineering pathways that will be understood for doing particular things, and then a lot will be kind of computationally irreducible in between. I'm kind of reminded of the first Blade Runner movie that I think opens with I haven't seen that movie since it came out, so my memory of it is a bit dim, but I seem to remember the beginning of it features a genetic designer who has all kinds of little devices in his house for, a creature that opens the door, a creature that does this, a creature that does that. That's an interesting vision. I think we're still quite a long way away from making that reality. And I think that will happen through having particular mechanisms where we can understand how to do the engineering, and then a lot of kind of computationally irreducible stuff sort of filled in around the edges, so that that thing that was supposed to open the door might usually do that, but it has enough sort of computational irreducibility in around the edges that it might also, jump on the table or something instead. I think that it's an interesting thing. Back, I don't know, 40 years ago or something, maybe close to 50, there were people who were confidently saying, this computer revolution, that's nothing. Just wait for the sort of biological revolution of things that one will be able to do by sort of creating custom biological organisms and so on. That hasn't really happened yet. I think that the place where that becomes important is that sort of since if we're interested in interfacing to us, we are biological organisms. And so the interface to us has to be, in a sense, biologically aligned. And there, I think we have more potential for sort of biotechnology of that sense, in that sense, to be important. Let's see. Left is commenting about growing neurons for a computer. Yeah, there's a company we've interacted with a bit that's growing brain organoids and trying to have them serve as computer components. It's really a challenge to communicate with that brain organoid and to train the brain organoid to do what you want. And I don't know. I think it's an interesting thing, particularly for neuroscience research, to be able to grow and do things with brain organoids. I doubt it's going to be a competitive thing for actual computing anytime soon. Let's see. Hill's comments. I've seen a lot of PhD students use ChatGPT to review my paper, and the comments are similar to what a real human would give. Yeah, I mean, insofar as commentary is sort of based on sort of the average of the population, I think that's what you're likely to get from an LLM. if you want the LLM to suddenly come up with a brilliant idea, oh, you missed this thing in your paper, you should have done that instead, I don't think the LLM is going to be the winner for that. Let's see. Nancy asks, is there a limit to automatic design of algorithms? Well, that's a complicated question because what does it mean to design an algorithm? So you have to know what the algorithm is supposed to do. So you have to have some specification language. You have to have some description of the algorithm that already exists. Now the question is, you're asking a little bit, if we can say, I want an algorithm that achieves these objectives, it's a little bit like the NP problems I was talking about earlier. We want to find a way to achieve this objective, but I'm not telling you how we're going to do it. Then, to what extent can we fill in the algorithm that you need to be able to do it? That's sort of an art that hasn't really developed that far. So, for example, you might say, let me give you 1,000 examples of what I want to have happen. Now make an algorithm that will generalize that. Neural networks do that, but they do that in a sort of fuzzy way for kinds of things that are a little bit like what we humans do things like that for. They don't, if you say, here are some examples of factoring, now, generalize that and be able to factor any number, it's not going to work. How do you get can you fill in, can you automatically discover an algorithm for factoring? For something as sophisticated as that, we absolutely do not know how to do that. For something like sorting, if you give me a fixed number of objects, let's say 16 objects, and you say you've got something where you're just going to compare object 1 with object 7, object 8 with object 11, object whatever with whatever. You're doing a sequence of pairwise comparisons. That's a case where it has been fairly successful to find optimal sorting networks just by searching the space of possible sorting networks. I think a couple of things that are interesting about that, the sort of engineered algorithms for sorting, if you looked at sort of the pattern of the comparisons they make, it's a fairly regular pattern. But if you just go search the space of all possible sorting algorithms, you can come in for a particular number of things you're trying to sort and say, this is the optimal sequence of comparisons that you have to make. Those optimal sequences look really pretty random. They do not look like engineered things. Sort of an interesting case where the optimal algorithm is one that you can sort of find by searching the computational universe, but you'd never engineer it. It's just too irregular, too random looking to engineer. In practice, I think the sorting network's the biggest one where we know the optimal network is 16 elements, which is not very big. But that's a case where sort of you can hope that you can find sort of ways to kind of find those kinds of algorithms by sort of automated searching for algorithms. Now, in fact, something I've done quite a bit is kind of searching the space of possible programs for algorithms for doing particular kinds of things. The big surprise is that if you search, like in fact, just last night, I burnt about 1,000 hours of computer time doing a big search for something, for a kind of a computational thing for which you can think of as being algorithms. I was just earlier today, I had left my computer running all night with a bunch of parallel computers running on this problem and giving back the results to my computer, and it generated all these pictures. And I was just starting to look through them to try and see whether it found something exciting, so to speak. That's an example of kind of automated algorithm search. I think really the state of the art for I have this problem I'm trying to solve with these constraints, make me an algorithm that does that. We don't know a lot about doing that, except in the case of sort of very fuzzy things like neural nets. I think that these things that I've done a bunch of just searching the computational universe of all possibilities and trying to see how that matches up with the things that one is trying to achieve, that's an interesting direction. And I've had quite a bit of success with that over the years, but there's vastly more that can be done in those directions. Let's see. Uh, um, let's see. Well, Woman asks, what are some technologies that modern civilization has adopted, developed, and invested so much into that while they might be inferior to alternatives, we're kind of stuck with them because of cultural ossification? I think it's not so much cultural ossification. I think it's that it's just this sort of economy of technology is such that when you've built this big stack, when you've optimized in this particular direction, it just takes so much effort to go in a different direction. I mean, we could think of a zillion kinds of standards for communication standards, uh, keyboard layouts, um, ways of representing numbers in computers. There are tons of things like that where just so much is based on them that it's kind of the cost of switching is way too high. And what's the value of switching? Let's talk about keyboard layouts. QWERTY is probably not the best keyboard layout. Move and the distribution of words in English and things like this. Um, there are better ones, but to use a better one, we'd all have to learn how to use that different keyboard. And it could be that in practice, the sort of total time to learn how to use the keyboard and so on, the sort of switching cost of having some keyboards in one form, some in another form, it just would never be worth it. So even though sort of there's a better endpoint, there isn't a um, that there isn't it's not realistic to get there. Now, it's interesting to compare that with biological evolution, because I was mentioning earlier, there may be this amazing organism that could be built that could be made with proteins and so on, but you just can't incrementally get there from organisms that already exist. I mean, a classic example of that is wheels, where there are microscopic organisms that have, flagella that rotate, but there aren't macroscopic organisms with wheels instead of legs. And people sometimes argue, well, wheels aren't that good because they don't go over rough terrain and so on. But I bet there are cases where wheels would be, deploy the wheels for that creature that's trying to run away from its predator and so on, would be a useful thing. But then there's a question of, well, maybe you just can't get there. Maybe you can't build a wheel with biological materials because, oh, you can't feed blood supply to a thing that's turning around, something like that. There might be a solution to that. Or maybe it's just it was really hard to get to macroscopic sized wheels from the biology we have. In other words, there wasn't a path that took us through organisms that wouldn't be total failures. And the same thing might be you could think of as true in the engineering domain, that you can get to a better place, but it goes through things which have such high cost that you'll never go there. Now, sometimes the probably it's the case that a different approach really would pay off. I mean, there's all these sort of fallacies of sunk costs and things and so on. Of when do you decide it's time to pay off the technological debt and build a new thing? I mean, it's something that comes up for us quite often in software engineering and so on. Of when is it worth just throwing away the old thing, building a new one, or retooling things versus sort of patching the old one. And for sure, there are sort of it's a complicated dynamics of the world, and it's a question of what you're optimizing for, whether it makes sense to do that. I mean, I'm trying to think about cases where sort of the path that's gone down. I mean, the fact that you might have the incantation HTTPS colon slash slash at the beginning of sort of going to every website. Well, in principle, that seems kind of silly. In practice, it doesn't really matter because web browsers just fill it in now. It's just like you could say, well, that's kind of inefficient. How can we deal with things like that? Well, it turns out there's then a layer of technology that comes on top of it, like, oh, you don't want long command names because they're so hard to type. But then you get autocomplete and it doesn't matter anymore. So I think papering over these things that are perhaps were not precisely the right initial choice. There's a question of whether the technology can paper them over, whether one should go back and redo it. And I'm sure there are better examples than I'm thinking of right now of places where sort of redoing it, becomes more and more difficult, but it really would have been a good idea. It's just we'd have to go back 100 years to do that. I mean, I'm kind of thinking that some of the things like laying cables in the ground and so on, where nobody actually knows where the cables are in city XYZ, it would have been better to put them in some kind of conduit so you know where all of them are and so on. But that wasn't a thing that was being thought about when the first electrical cables were being buried and first telephone cables were being buried. And now it's easier to sort of have an overlay on that than to go back and fix it. Let's see. Aardvark is asking, what will be the next big thing after AI? So I know what to learn about. What will be the next big thing? Well, I've been saying for a while, I think robotics, humanoid robotics and things will be a big thing, but that will be rather driven by AI. I think the kinds of things that, let me say the following. There are things where there is technology that I think is inexorably going to come at some point, but it's super hard to say when. And I think one could be wrong by 100 years. So, and that's true of lots of technology of modern times. Some of it was portrayed in science fiction, half a century or a century ago. It's just very difficult to know when it will come. I mean, I think a bunch of kind of molecular scale technology and things, chemistry is about kind of having chemical reactions where molecules sort of randomly bump into each other and will connect, modify each other or whatever else. Biology seems to have figured out a lot better how to sort of have this bulk orchestration of how molecules move around to achieve certain objectives and so on. My guess is that there will be, by some method, whether it's in solid state, whether it's not, by some method, there will be sort of ways to have things happen at a molecular scale that are like computing and under our sort of engineering control. That will eventually be a big thing. I don't know when. I've been waiting for that one for 45 years. And I don't, there's sort of intermediate technology that one could imagine building to get to that point, but we're not really there yet. I mean, there are things, and when we do get that kind of thing, there are an incredible number of sort of interfaces to our biological existence that will be very important for that. And I think that will allow sort of a bunch of biomedical advances of sort of fixing different things in humans sort of better than the immune system and patching things up and going and sending in the nanobots to go repair that particular piece of tissue or whatever else. There are just lots of kinds of things that would happen sort of at the hardware level then, but that hasn't been unlocked yet. I mentioned, what tends to unlock new things is some new methodology that suddenly starts to work, like LLMs suddenly started to work, and that's led to lots of new things. If somebody was able to do, let's say, gene sequencing vastly faster, cheaper than it's done right now, so it routinely becomes possible to just, sequence every piece of fish you're about to eat or something, or sequence your immune system every day to figure out, what's happening in your body type thing. These kinds of things. You could imagine once that technology gets opened up, that a huge torrent of possibilities will occur as a result of that. And that's usually the thing, that some methodology suddenly starts to work, and then there's a torrent of things that happen. The big methodology that I've been sort of making use of is kind of this computational paradigm, the idea of sort of formalizing things in terms of computation. That's the thing that sort of Wolfram language is based on. That's the thing I've been sort of trying to do all these years, is make this kind of computational notation for talking about the world. And what that computational notation enables is a computational X for all fields X. And over time, different fields X start to suddenly get a computational X. And those are other kinds of that's a case where there's an overarching methodology of sort of applying the computational paradigm, using our computational language, for example, as the path to be able to do that, and then being able to go and take those ideas and feed them into this or that field that has not been sort of enabled by that kind of methodology. And those are big new things that will happen. Each one of them takes kind of the seeing how to connect kind of this new paradigm into an existing field. I mean, it's that just you can, it's something where it's going to require creativity to make that connection. Once that connection is made, you can then take all the things that have been developed in this computational paradigm and immediately start applying them to this area or that. And that's what I've been doing in the last few years, particularly from our physics project, applying kind of the ideas from the paradigm that emerges from our physics project and applying them to things like the foundations of machine learning, foundations of biological evolution. I'm hoping soon foundations of economics, foundations of neuroscience, etc. These are all things where sort of things are getting opened up, and there are lots of possibilities there. But those are things on the conceptual side. There are also things on the kind of what's hardware possible side. And it's a good question, sort of, if you make some particular kind of thing 1,000 times faster, cheaper, whatever, how does that change the world? And then the question is, well, can you actually do that? Make the thing, faster, cheaper, whatever. And that may be something that's very hard to predict. Some of those things, it's like it's probably possible, but it's really hard to predict. I mean, maybe it'll be, maybe nuclear fusion will be cracked. There are there's a path to do it, but there are lots of practical problems. Or maybe cold fusion will turn out to work. I kind of think there is a way to do that. And, it'll be discovered it isn't, dissolving hydrogen and palladium, which was the original idea that everybody said was nonsense, although I'm not as convinced about that myself. Maybe suddenly somebody will discover that if it's just this alloy of palladium that has this characteristic and you feed the hydrogen in just this way, those hydrogen atoms will get close enough that they'll start undergoing fusion. Of course, what happens then to the material once you've got fusion happening and neutrons spraying out, I don't really know. But in any case, that's it's maybe cold fusion will get discovered. If that happens, then all sorts of things get enabled as sort of a vast thing that gets opened up of things where sort of it's trivial to get power to lots of things where that wasn't possible before. Let's see. All right, maybe one more question, then I have to go back to my day job. Okay, Latch asks, do you think there'll be in the short to midterm an AI architecture that manages to synthesize mental images to the level most humans do? Visual spatial kinds of patterns. I mean, if you mean by that, will AIs produce images that seem as realistic as the things we see with our eyes? For sure, that will happen. It's already happened to some extent. The mental images that we conjure up, we have a very hard time knowing quite what they are. We can describe them. I'm imagining, a purple cone or something, or I imagine this thing where this happened. But it's mostly taking a mental image, which is somehow formed in our brains, and verbalizing it in a very coarse way with words. So I don't think we know what our mental images are. You could try to use functional MRI, for example, to go and look at activity in one's brain and try and deduce what images one's thinking about from that. There are a number of experiments that have been done on that, and there's some enthusiasm these days for brain-computer interfaces that could be basically thought-to-picture type interfaces rather than text-to-image. You've got thought-to-image. That hasn't worked yet in a serious way. Will it work? I'm a bit skeptical, actually, because I think that when we think of something, the unformed thoughts in our minds are unformed. They really don't get to be a thing that's transmittable to anybody or anything else. They're and that really it's only once we've got that thought to the level where we can start to verbalize it that the thought is formed enough that it is communicable. So I think, we say we imagine a mental image, but we, I don't know. Maybe I'm just bad at doing mental imagery. I don't know. Um, there are people who have very different levels of performance and things like being able to do 3D mental rotation. Given that you have one of my kids, for example, is very good at this. Given that you have an object, and it has this shape, what happens if you were to rotate it? What would it look like, and so on? I can't do that at all. But some people can do that well. And I think, and perhaps I'm impoverished in terms of mental images. I mean, one of the sad things about the field of mental imagery in neuroscience is one of the people who was a prominent researcher in that area also just didn't form mental images really, and came to all kinds of conclusions in that field based on that fact, even though other people have a different experience. I mean, just like some people have synesthesia, where given a letter you think of a color and so on. And again, one of my kids, a different kid, has that. And I've always been meaning to go back and try and see whether the sort of early learning of letters happened to be on some board that had an A in green and a B in purple or something, and whether that's how the synesthesia got developed. I've no idea. Or whether it's really a brain connection type thing of this shape is sort of close to this set of sort of things that are perceived from color receptors and so on. But this whole question of sort of, can we emulate the mental image? I think the only thing we really know is, can we make an image that, when transmitted through our eyes, will have the sort of sensation of a certain kind of image? And that we're well on the way to doing. If we ask about brain-computer interfaces where we're picking things up from the innards of our brains, and turning those things into sort of visible, eye-seeable images, that's an interesting possibility. If we imagine sort of the other way around, of sort of sort of stimulating our brains to see a particular image, I think that's far away at this point, very far away. I think the moment when the deep brain stimulation, array of electrodes is going to cause us to imagine this elaborate scene, I don't think that's near at hand. I mean, of course, one knows that in, I don't know, neurosurgery and things, when you sort of excite a particular spot in the brain, you can end up having particular verbal responses to that. So, but I think that's a little bit of a different thing. I think that's something where you're kind of stimulating. I don't really understand that phenomenon. I don't know to what extent it's a reproducible phenomenon. And it's very difficult to do reproducible experiments on brains because they learn. I mean, if you say it's like, you go to an optometrist or something, and they say, can you read off these letters? Which line can you read? And I certainly remember in the distant past just saying, they say, wow, you can read so many lines, and that it's like, it's the same chart. I just saw it with a different lens. I have a good memory. I remember these letters. I learnt it, so it isn't a good test anymore. So those experiments are difficult to do. All right, I think I should uh, wrap up. I'm sorry, I have to. There's one last question here from Weasel. Do you think there will ever be a decent food 3D printer in the future, as promised? I think the chocolate was the only thing that ended up being viable. I've seen these printers, these sugar printers, and I seem to remember at one event we did, we had some 3D printed chocolate thingies. But yeah, I haven't seen that. I have to say, it's one would think that the sort of the very high-end restaurant or something would start to have 3D printed food, or that one would have sort of for our company, we have this 3D logo, the spiky object, the rhombic hexacantahedron, and it's very 3D printable. And making sort of 3D printed sort of food stuff in that shape would seem like a natural thing to do. I think yeah, I haven't seen that. I don't know what the issues are there. I think 3D printing in general has sort of segued into there's sort of professional 3D printing of printing things for medical purposes, teeth, bones, things like this, or printing things that are sort of weird shaped blades for turbines or something like that. There's sort of the professional 3D printing world, which has very much taken off. But and then there's the very amateur, it's just a cute thing to be able to print this thing out of rather crummy plastic 3D printing world. The intermediate scale of that seems to have more or less vanished. I mean, I needed to 3D print something, a year or so ago, and it was a fairly elaborate thing. And I had a very hard time with that. I was trying to print something kind of complicated. It was in multiple colors, et cetera, et cetera, et cetera. And all these companies that used to exist that did that have disappeared. And it's like, well, do you want a production run of 10,000 of those things? Not, oh, we can just run off this 3D printout. I do have to say, in terms of making shapes of things, I'm going to tell two stories, and then I really have to wrap up. One was an early sort of conference about new kind of science from 20 years ago or something now, where we had a cake made in a 3D cellular automaton shape with, I think that was not explicitly 3D printing, that was more just hand assembly and things. The problem was the sort of cake engineering had not been done adequately, and it was a very sad, sorry thing because this very lovely pyramidal cake just sort of crumbled before one's eyes so that was one sort of shapes are hard type thing. I have to tell another story from the beginning of the 1990s when we were making a trade show booth for our company, and we wanted to kind of fly a balloon up above the trade show booth. And we had contacted some company. I mean, I wasn't the frontline person doing this, but actually the person who was the frontline person was a fairly sophisticated mathematical person. We'd contacted this company, and we really wanted to make a knot, some trefoil knot or something, as the shape that we would have as our balloon, a helium balloon above our booth if the trade show allowed such a thing. So this company contacted them, and they were like, "Yes, we can make a balloon in any shape. We've made chickens, we've made bananas, we've made any shape." And then we sent them this truffle knot, and they're like very, very confused. Because in fact, what they meant was any shape that is sort of continuously deformable from a sphere. But that level of sort of mathematical sort of thinking about shapes probably was something that had absolutely never come up in their business. But it's just one of those stories of we can make a balloon in any shape. We can 3D print food in any shape, so to speak. Well, there end up being these practical problems about what you can do. But yeah, I wonder what's happened to the food printers. I think, the fundamental problem of 3D printing at some level is it's still kind of messy. You build things and you get a lot of little granules there, and you have to brush them off, and you have to clean things and so on. My guess is with things that are edible, that makes it all gets very complicated. I mean, we know people who decorate cakes have something, have a nozzle that they're squirting icing out of, and that's not that different from a 3D printer nozzle. But my guess is that if you try and do that on a large scale, the thing gets very messy. And I'm sure if you're a cake decorator, you kind of know you can do it for a little while, and you have to clean the thing and so on. And probably for a 3D printer, I don't know how that works. I mean, one could imagine the printer would squirt whatever it is, sugar through the nozzle for a while, and then we'll go into some kind of cleaning cycle and go back to doing it. I don't know why that hasn't happened more. A good question. I should check it out. All right. Well, thanks for lots of interesting questions there. It was fun to try and answer these with you guys. And I look forward to chatting with you another time. Bye for now.